Hi, Chem Peeps. Today we're going to talk about Dalton's partial pressure. And this is a really important law to use when you're collecting a gas over water. You know, in our atmosphere we have many gases: carbon dioxide, nitrogen, hydrogen, oxygen. We also have water vapor. And when we're collecting a gas over water, maybe we're bubbling a gas we're collecting in lab up through the water into a test tube. You're going to have more than just that gas in the test tube. You're also going to have water vapor, because the top of the surface of the water, there will be some molecules that escape from the liquid phase into the vapor phase, and they're going to be part of what's in that sample. So you can see in this law right here, the total pressure, PT, is total pressure, is equal to the pressure of the gas, PG, plus the pressure of the water vapor. So this is total, and that's what would be in that test tube that we're collecting. This is the gas that we are collecting in that test tube, and then of course this is going to be water vapor. We have to account for that so that our answer actually is accurate. So if we look at the other things I have on the screen, we're going to be using the combined gas law today. And I forgot to put my division line here in here, so let's go ahead and do that. And with the gas law that for combined, we're going to use pressure, volume, and temperature, both for gas 1, that's what the 1s represent, and gas 2, which is the second gas condition. I apologize that my 1s and 2s are not subscripted in the formula, having issues with my software currently. Over here, I have standard temperature and pressure conditions for our gas, and that will come to play in our problem when we read it. So let's look at the problem. It says a sample of oxygen collected over water. That's your key right there, that you are going to have to use Dalton's partial pressure when the atmospheric pressure is 1.002 atmospheres. So this is the total pressure because it's collected over water. The oxygen is mixed with the water vapor at a room temperature of 25.5 degrees Celsius, so that's T1, and occupies 105.8 milliliters. This is V1. Now, one of the things I tell my students to remember is that the units you use for pressure or gas 1 must equal the units that you use for pressure or gas 2. So pressures must be the same unit, volume must be the same unit, and temperature must be the same unit, and temperature must be in Kelvin. So if you don't remember, Kelvin equals Celsius plus 273. So we will have to correct that value given to us so that it is in Kelvin. So let's continue here. It says, what will be the volume? So that's going to be volume 2 of this dry gas. So we want just the oxygen gas at standard conditions. So STP means that temperature 2 is going to be 273, and pressure 2, look here, is going to be an atmosphere, so it's going to be 1 atmosphere. And I'm getting both these values up here for the values that we know that exist at standard temperature pressure for gas. Now notice this. This comes from a chart. Water vapor will increase or decrease based upon what the atmospheric pressure is. And so if we look here, the water vapor pressure at 25.5 degrees Celsius is 0.326 atmospheres. So I need to do this problem correctly, I need to know the pressure of the gas. I need to solve for this first. So the total pressure was 1.002 atmospheres. And I don't know the pressure of our oxygen. That's only unknown. And the water vapor is told to me to be 0.326 atmospheres. So the pressure of our gas, which is going to be pressure 1 in this problem, if we do this math, is going to be 0.676 atmospheres. So let's go ahead and set up this problem. Oh, we also need to do a temperature. So if I deal with this, my Kelvin temperature is going to be 25.5 degrees Celsius plus that 273. So my temperature 1 in Kelvin, this will be temperature 1, is going to be 298.5 Kelvin. All right, so now let's set up our problem. So if we set up the problem, I'm going to change the color here just so we're not confused. Our first pressure is 1.00. Nope. See, I went ahead and tried to do that. It's going to be this. Oh, I erased it. Darn it. It was 676 atmospheres. So when I put it in, it's going to be 0.676 atmospheres times the volume, which is 105.8 milliliters, all over the temperature that we corrected to be 298.5 degrees Kelvin. And when I solve the second side, my pressure is going to be 1 atmosphere because it's at STP. And my volume is unknown. And my temperature is 273 because it's an STP. To solve this problem, I'm going to take this top times this bottom and set it equal to this top times this bottom. So when we set this up, we are going to get 0.676 atmospheres times 105.8 milliliters times 273K, and it's going to equal 298.5K times the 1 atmosphere times volume 2. Now we're trying to solve this volume 2, so we're going to divide both sides by the 298.5K and the 1 atmosphere. And when we do that, volume 2 comes out to be 65.4 milliliters. And that is going to be our final answer. I hope this helps you using Dalton's partial pressure and have a better understanding of using that to solve for a variable in a formula. You can find more videos on gas laws on TikTok and YouTube at Ken's Chem Chat. Please like and leave me a comment if you have questions or need to see something more. I will see you later.